All right, today we're going to get a grip on a really big challenge, one that's shaping the entire future of robotics. And you know what? It all starts with a surprisingly delicate problem.
I mean, it sounds like a simple question, right? But it actually gets to the very heart of a huge challenge in robotics. See, we tend to think of robots as these super strong, super precise machines. But when you ask one to do something that requires a delicate touch, like picking up something fragile or an object with a weird shape, well, they're pretty much all thumbs. And that's because most of the grippers they use are really rigid and powerful, but they just aren't very gentle. And this comparison really lays it all out, doesn't it? It's basically a story of brute force versus a smart, gentle touch. On one side, you've got those powerful but, let's be honest, clumsy, rigid grippers. And on the other, you have these gentle and incredibly adaptable soft grippers. So it kind of makes you wonder, what if we could build a robot with a grip that was a lot more like our own? Okay, so let's dig into this problem with rigid robots a bit more. I mean, don't get me wrong, they're fantastic for certain jobs. If you need something to pick up the exact same car part thousands of times a day in a factory, they're perfect. But the second you ask them to handle something fragile or something with an odd shape, they just struggle. And that is the technological gap that really sparked this whole quest for something better. And that quest, well, it brings us right here, to a softer, smarter kind of grip. This is the hero of our story today, the soft robotic gripper. So what makes these things so special? Well, it really comes down to their design. A lot of them are actually inspired by nature, things like an octopus's tentacle or even the human hand. And because of that, they can literally conform to an object's shape, spreading the force out evenly and gently. So to really get how they work, we need to look at two key things. First, how do they actually move? And second, what in the world are they made of? First up, let's talk about movement. And right away, you can forget about motors and gears. This is all about some really clever physics. The key concept here is something called actuation. Now, that's just a fancy word for what produces motion. You can think of it as the muscle of the soft robot. And believe me, there are some truly fascinating ways to power these muscles. So the most common way to do this is with something called fluid actuation. Basically, it uses air or water pressure to inflate these little channels inside the gripper, which makes it bend and grasp an object, kind of like a high-tech balloon animal. And this method is so effective, it's actually been used for deep-sea exploration. We're talking about operating successfully at depths of over 2,300 meters. That is just incredible. Okay, now check this out, because this is a really fascinating concept. This quote is talking about a type of gripper that works kind of like a beanbag. So it's soft and it can wrap around pretty much any shape. But then, and this is the cool part, a vacuum is applied and all the little particles inside jam together, making it instantly rock solid. It can grip something super firmly and then, just as quickly, soften up to let it go. And it's not just air and beanbags. This just shows you the sheer variety of ways we can make these things move. You've got grippers inspired by the Venus flytrap, artificial muscles powered by electricity that are so gentle they can lift a raw egg yolk without breaking it. And get this, thermal grippers that weigh less than 3 grams but can lift almost 3 kilograms. That's insane. And having all this variety is so important because it means we can build the absolute perfect gripper for any specific job. Okay, so we've got the movement down, but what are they actually made of? That brings us to the materials. And honestly, this is where the real magic happens. Because we're not just talking about simple rubber or plastic here. We're talking about smart materials. I mean, the materials are really the heart and soul of the gripper. You've got things like hydrogels, which are over 90% water, so they're basically invisible underwater. Then there are polymers that can stretch to an incredible 6 times their original length. It's amazing stuff. So let's take a closer look at one of these core concepts. So what does this process, shape memory, actually give us? In a word, programmability. You can have a material with a set, remembered shape. Then you can deform it completely. But as soon as you apply a simple trigger, like a little bit of heat, bam, it snaps right back to its original form. And that is absolutely perfect for a reliable grip and release mechanism. Okay, so we've got the clever movement, we've got the magic materials, so what? What does this all add up to? Where's the big payoff? Well, the payoff is that we're already seeing these grippers in action pretty much everywhere. In industrial automation, some of them can pick over 90 items a minute. They're out in the fields being used to harvest delicate fruit like apples. And they hold just massive potential in fields like minimally invasive surgery or handling really sensitive biological samples. But the journey is definitely not over. It's not perfect, yet. There are still some pretty major challenges to solve. Right now, there's often this big trade-off. Yeah, you can get absolutely incredible performance from a gripper, but that might come with a really high price tag, or it might be made of materials that just aren't durable enough for heavy-duty, long-term industrial use. So, looking ahead, the big focus for researchers is on solving exactly these challenges. They're working on making the grippers more self-contained, without bulky pumps and power sources. They're trying to make them tougher, more dexterous, closer to a human hand, and of course, cheaper to produce. A lot of times using really cool new techniques like 3D printing.
And all of this really brings us to a final big picture thought. What actually happens when machines finally have a human touch? Because as this technology continues to mature, it's going to fundamentally change our relationship with machines. It's going to unlock possibilities in medicine, in exploration, and in our daily lives. Possibilities that right now we are only just beginning to imagine.